Welcome to the next chapter of our lecture on channel codes, graph-based codes. And after we have introduced the concept of block codes in depth, now we are going to look at a specific instance of block codes. These are low-density parity-check codes. And this chapter is divided into several sub-chapters. In this very first video, we are going to look at simple parity-check codes, and then we are going to specialize this to the class of low-density parity-check codes. And then we are going to look at how to decode them before we then analyze the codes in the next chapter. So let's start with this chapter on parity-check codes. So what is a parity-check code? So if we recall what we know so far, we have seen various constructions of codes. We have seen repetition codes, we have seen Hamming codes, and if you may recall from other lectures, the BCH codes or Reed-Solomon codes, you may know product codes, and they are all very deterministic constructions. And these are very classical schemes, so BCH codes, Reed-Solomon codes are classically introduced codes in the 1950s, 1960s, and they are very powerful, but they have some advantages. So these codes, they do not scale when we increase n. So you can actually prove that if you increase n, either the minimum distance goes to 0, or the relative minimum distance goes to 0, or the rate goes to 0. So you cannot use them for long codes. And we have seen in order to get to the capacity, we need long codes, because we recall that the finite length capacity, or the rate that we can achieve, is approximately equal to the capacity of the channel minus square root of channel dispersion divided by the length n of the code times inverse Q function of the target error probability. And we know that in order to make this penalty term small, we need to make n large, because we cannot control the dispersion of the channel. That's a constant that is given. We cannot control PE, because that's what our system design tells us what we need to have. So the only thing we can control is n, and we need to make n as small as possible in order to have a low error probability. So we need codes for with a large n. We cannot construct them using classical schemes. Also, another classical scheme is a Reed-Solomon code, and the complexity of the Reed-Solomon codes increases with n. And there is also no decoding algorithm for binary input AWGN channels, so we need different codes. Then also these classical codes, they are only defined for some combinations of k and n, so you are not free to choose. So you always need to make a compromise depending on your overall system design. So we need new schemes, and we need new code constructions. And we saw that randomly constructed codes actually work pretty well. When we did the channel coding theorem, we looked at randomly constructed code. So this random construction that comes from information theory as an argument actually leads to very good code. So why not do a randomized code? And what we're going to do is we're going to look at randomized codes, but from a linear code point of view. So we construct a code based on a parity-check matrix, on a generator matrix, but randomly constructed. So that's what we do. So we define parity-check codes. So the codes that we encoded so far, they were defined by the generator matrix, but we know that we can also define a code by the parity-check matrix. Recall the code C is the set of all vectors x of length n that are binary. All binary vectors of length n such that parity-check matrix H times x transposed is equal to 0. That's an alternative definition of a code. So if we have a parity-check matrix, we can find all the x by checking which x's belong to the kernel of H or the null space of H. We can define a code by its parity-check matrix only. And from the parity-check matrix, we can get the generator matrix because we know that G times H transposed must be equal to the 0. So we just can do, for instance, Gaussian elimination, and then we find the generator matrix. Okay, so we define a code by the parity-check matrix. And what we do now, we define a random parity-check matrix. So the random parity-check code, and it's not a specific code, but it's a code ensemble. What is the difference between a code and a code ensemble? So here we're talking about ensembles. A code is a very deterministic instance. An ensemble is a set of codes. So it's not one code, but it's a big set of codes that are constructed using the same rules. And that's when we talk about ensembles. So we are not looking at a specific code, but we are looking at a family of code, which we call ensemble. And these family, they share structural properties. So the random parity-check code ensemble is the following. So we have a code of length n, and it's defined by a parity-check matrix H of dimension m times n. And the entries are randomly selected to be either 0 or 1. So what we do is we take a coin, we toss a coin, and if it's heads, then we take a 0. If it's tails, we take a 1. And we do this for every m times n entries of the parity-check matrix. So the entries of the parity-check matrix are selected to be 0 or 1 with probability 1/2. The idea is, of course, going back to Shannon, we use random codes in Shannon's. We saw that linear codes are nice codes because they help us with representing the codes in a nice way using a matrix. So we take this random idea to linear codes and we define random parity-check codes. So let's take a look at some properties. So the first thing we are interested in is the rate of the code. So we have to be a little bit careful because of the following fact. So if we have a parity-check matrix H of size m times n, then if we recall linear algebra, the number of independent rows in H is the rank of H. So we count how many rows are linearly independent. Because it may happen that because of this random construction, 2 rows are the same, or 1 row and another row is the 3rd row. These will actually, if 2 rows are the same, they will not contribute anything to the code, because the code essentially is the set of all x that are orthogonal to H or belong to the kernel of H. So we need to know how many possible x there are, and this is determined by the rank, because the rank tells us what is the dimension of the subspace that the kernel spans. So we know the rank is smaller or equal than the minimum of m and n, and we always say that the matrix is shallow. So we have n bits in our code word, and we have m parity-check equations. Because each equation defines, or each equation gives an equation or constraint on a few bits in the code word. And these are the parity-check equations that we always have less than n. So now, because the code X is the set of all objects, so just let me write this again. So the code C, okay. C is the set of all X, element F2, power n, such that H times X transpose is equal to 0. So now how many different X do we have? Well, that's given by the rank of H, by the dimension of the subspace. So the possible number of X is given by the effective dimension of the subspace, and that is K equals N minus the rank of H. So the rank of H tells us the number of effective information bits, because K is equal to log 2 of the cardinality of the code. And then depending on for how many X this equation is fulfilled, then of course K is given by log 2 of the set. If we only have one effective equation that fulfilled, then we only have one X. Two effective ones, and we have possibly 4 different X. So that tells us how many information bits we have. Now, because the rank is upper bounded by M, the number of information bits is larger or equal than N minus M. So now we can define the rate of the code, and unfortunately it doesn't look as nice, because the rate of the code K over N is equal to N minus the rank of H over N, or 1 minus the rank of H divided by N. So the rate of the code depends actually on the rank of the Parity-check matrix. And that's a little bit unfortunate, because it's a number that depends on the realization of the code, and that we always need to check. But we can give a bound. We can say the rate is larger or equal than 1 minus M over N. And this is what we call the design rate. This is what we call RD, and RD is the so-called design rate of the code. So what's the design rate? The design rate of the code that's defined by Parity-check matrix is 1 minus M over N. And that's a lower bound on the real rate. The design rate is nice because it tells us the dimensions of the Parity-check matrix, and it tells us the real rate is going to be larger or equal than the design rate. So this is the design rate, but the real rate depends on the rank of H. Okay, so now we are interested in how big is this difference? So is the rate significantly larger than design rate, or are they equal? So that's something we're going to do next. First, here is an example. So I took a random number generator, and I generate a code of size 12 times 24. And this comes immediately from the random number generation. And we can calculate the rate. So if you have, for instance, MATLAB, that's tremendously easy. So in MATLAB, you just calculate, you have a binary matrix, you calculate rank of GF of H, and it will give you the rank. So what the command GF is doing, GF transforms the matrix H into a Galois field, which is binary numbers. So if you just put GF, you restrict H to be binary numbers. Then you calculate the rank, and MATLAB knows, okay, this is a matrix that is binary, that is defined over F2, which is GF. And we can calculate the rank of this matrix. It's equal to 12. So it's equal to M, and the rate is equal to design rate. So was I lucky? Did I construct this matrix, and by a 1 out of a million chance I construct a matrix with full rank? Shall I play lotto with this matrix? Well, no, it was pretty natural to have a full rank matrix. So let's take a closer look. So let's take a closer look at the rank of a binary matrix. So we start looking at the number of binary matrices of a given rank. And that's we have the following lemma. So we start with binary matrix of size M times N. We assume that M is upper bounded by N. And then we have RF of M and N denotes the number of matrices that have of size M times N that have full rank, hence F. Rf is the number of binary matrices of size m times n, and with rank m. And we can give a simple expression for this. So Rf is 2 to the power m times n times the product from 0 to m minus 1, 1 minus 2 to the power I minus n. That's the expression for the rank. If you would like to see the proof, you can go to the very end of the slides, and there is a few pages with the proof of this theorem, this lemma. It's actually pretty easy to prove this. It is essentially just counting. So we just count how many possibilities do we have for filling the first row. Then, given that we have filled the first row of the matrix, how many possibilities do we have of filling up the second row? Essentially all the possible binary vectors minus the one that is already in the first row. Then for the third row, we need to rule out the first row, the second row, and the combination of the two rows. So we just always rule out all possible combinations. And then with some manipulations using the binomial theorem, we can get to this expression. So it's just 1 or 2 pages of a little bit of combinatorics. Okay, so this is the result of the number of matrices of a given rank. So now what is the probability that when we randomly construct a matrix that it has full rank? So we start with the constructed binary matrices with random probability. And the probability that H has full rank, just a Laplace experiment. So we count the number of matrices that have full rank and divide by the possible number of outcomes, or possible number of realizations. This is 2 power m n. So the probability that the matrix has full rank is given by this expression. So it's the product from j equals 0 to m minus 1, 1 minus 2 power j minus n. And what we see now is that if n goes to infinity, if we let n get very large, this guy becomes very, very small. This guy becomes negligibly small. It's just 2 to the power minus n. M is smaller than n, so this will always be negative. This will always be very small, and this will essentially just be the product of ones. So in the limit, the probability that the matrix has full rank will approach 1. So how fast do we attain this limit? Well, for this, we plot the probabilities. So if you want to play around with this a little bit, we have a MATLAB file, rank of random binary matrix. I just have a random number generator, construct a matrix, and calculate the rank. So you can play around with this. It's just a few lines of MATLAB code, and then you get the rank of the matrix. So we're going to look at 3 different cases. So we're going to look at case 1. We have a matrix of size m equals n divided by 4. Calculate the design rate. This is 1 minus m over n. So this is 1 minus 1 over 4. It's 3 over 4. So it's a matrix that looks like this. So that's the Parity-check matrix H. There's 1/4 row and 4/4 columns, so to say. That's the first case. The second case, you're going to use a different color because it's the colors that are going to be used in the figure. So I have case 2. M is equal to n divided by 2. In this case, the design rate is 1 minus m over n, 1 minus 1/2. So this is 1/2. And the Parity-check matrix looks like this. And we have a case 3. M is equal to 3 over 4 times n. And the design rate RD is 1 minus m over n. Is equal to 1 minus 3 over 4. So it's 1 over 4. And the parity-check matrix looks like this. And then we calculate the probability that the different matrices have full rank. Which one do you believe attains a full rank earliest? Stop the video here and think about this for a moment. So if you think about this, then it makes sense. This matrix has the possibly highest probability of a full rank because we all just have a very few rows to fill. The probability that we have 2 to the power n possible vectors to put in the rows. So the probability that we choose a vector that is linearly dependent on the previous vectors is rather small. Then here it's already, we need to fill more vectors, and here we need to fill quite a lot of vectors in the matrix. So the probability that we select a random vector for a row that has already been used is quite high. So we expect the probability having a full rank to be smaller. So let's evaluate the equations and let's take a look at what we get. And this is what we get. So as expected, we approach 1. So here we show the probability that we have a full rank as a function of the length of the code n. So for the rate 3 over 4 code, we approach 1 very rapidly, and already for length 15, we have a probability that is close to 1 of having a full rank matrix. For the rate 1/2 code, also here we see a probability that is close to 1, is significantly larger than 0.99. And only for the rate 1 over 4 code, the convergence is slower. But already for length 40, we are also close to having a rate of 1. So this is the rank of random binary matrix. And what we can conclude is that if n is large enough, probability that H is full rank approaches 1, and it has as a consequence that the design rate is almost equal to the rate of the code. So it suffices to calculate with the easier design rate with a very high probability you have a code that has the same rate. Of course, if you want to go into production with this code, you will need to double check if this is really the case. Okay. So now we're going to look at the weight enumerator of parity-check codes. And we have the following theorem. And that's a lot of math on this slide. We're going to dissect this a little bit. So we recall the weight enumerator. So AW is essentially the number of code words from our code X. So it's we have a set, take a set of code words such that the weight of code word X is equal to W. And we count the number of code words where this happens. Now we have an ensemble. So now we don't look at a specific code, but we look at all the codes that are constructed using the rules from this ensemble. And then we have an average weight enumerator. So if we construct all the possible codes from this ensemble, we calculate the weight enumerator. What's it going to be on average? That's the average weight enumerator. So that's AW, that's the average number of code words in a code, averaged over all the possible parity-check matrices constructed according to our rule. So with the probability that Hij is equal to 0 being equal to 1/2. And with the design rate, RD is 1 minus m over n. The average weight numerator is n over n choose w times 2 to the power minus n times 1 minus the design rate. And because this is a function that is nice and clean, but numerically difficult to evaluate, because when n gets very large, this binomial coefficient explodes essentially. So we bound this binomial coefficient, and this binomial coefficient can be bounded using the Stirling approximation, and that's given by this expression, where we have the binary entropy function that we know from the capacity of the binary symmetric channel inside. So we're not going to prove this part. For this, you can also see the supplementary material in the back of the slides. We're going to quickly look at how to get to this part, because that's the one that helps us in our thinking of the codes. And then getting from here to here, it's just technical. It's just applying the Stirling approximation to the binomial coefficients or to the factorials inside the binomial coefficients and simplifying and manipulating a lot. And that's not too insightful. So I put this in the supplementary material. If you are interested, you're welcome to check it. It certainly doesn't hurt, but it's not something that is relevant for the course. But let's take a look at this guy and how we can show this guy. So for this, we define probability PW. So PW is the probability that a sequence or vector of weight W is a code word. So if W is equal to 0, that's easy, because then P0 is equal to 1, because the all 0 code word is always a code word of a linear code. We have a linear code, so we know the code word with zeros is always a code word of a linear code. So now the interesting case is if W is larger than 0. So now we're looking at the parity-check matrix H. And H is composed of parity-check equations, H1, H2, up to Hm. And now we ask ourselves the question, what is the probability that this sequence fulfills the first parity-check equation? Meaning, parity equation is fulfilled if Hj times x transposed is equal to 0. So what is the probability that Hj times x transposed is equal to 0? So a particular sequence of, or a particular, no, let's formulate it differently, a particular parity-check equation is fulfilled with probability 1/2. That's a little bit odd, but it's actually, if you think a little bit about it, it's not so hard to see. So we're looking at on the last position, where x, what we call the weight of x, is equal to w, has a 1. So if we calculate this, this is equal to the sum of j from 0 to n of h or l, hjl times xl must be equal to 0. So we're now looking at the last position where xl is equal to 1. And the sum up to there is either 0 or 1. We don't know it, but it's either 0 or 1. Now the last position determines if the result is 0 or is 1. So depending on what has come before, either we need a 1 or a 0 to make the result equal to 0. So now we're looking at the last position where xl is equal to 1. And now a 1 needs to happen here or not. But the 1 happens here with probability 1/2. So with probability 1/2, we get 0 in the last position, or with probability 1/2, we get 1. And what has come before also happened with probability 1/2 before, because everything, all the ages happen with probability 1/2. So it just depends on the last position. And the last position then is equal, h is equal to 1 with probability 1/2. So the probability that we fulfill a certain parity-check equation is actually equal to 1/2. So then the total number of check equations, one color, so the total number of check equations is n equals to n times 1 minus the design rate. Because if you recall, design rate RD is equal to 1 minus m over n. So it's just rearranging this equation a little. So the probability that the specific sequence of weight W is a code word is equal to 1/2 to the power m. So all the m parity-check equations must be fulfilled. Each one is fulfilled with probability 1/2. So the total probability is 1/2 to the power m. So it's 2 power minus m, or 2 power minus n times 1 minus the rate RD. Okay, so now we can calculate the average weight enumerator, because we know there are a total number of n choose W sequences of weight W. How many sequences of weight W are actually code word? And that's what the weight enumerator tells us. So the weight enumerator A W, and we call that average weight enumerator, is equal to the number of sequences of weight W that we have times the probability that the certain sequence is actually a code word. So it's equal to NW times 2 to the power minus n times 1 minus the design rate. And that's the average weight enumerator. So it's a little bit tricky if you need to think about how to get there, but it's just taking a simple expectation. And because of numerical reasons, this binomial coefficients is usually not very nice to calculate. We do this upper bound, which is rather technical and also not very insightful, but that's for that we refer to the supplementary material. Okay, so let's go ahead. So now we're looking at a further result, and this further result is the following. That's also taking some time to digest, and that's the distance distribution. So now we ask ourselves, we have constructed a parity-check code of dimension m times n, and we're looking at what is the probability that the minimum distance has a certain value. And we're looking at the distribution function. So looking at the probability that the minimum distance is smaller or equal than some constant. So just as in a CDF type of argument. What is the probability that we are below, that the minimum distance is below a certain constant? And we assume that this constant is a factor of n. So delta is a number between 0 and 1/2, and delta n is an integer. Why 1/2? Because it doesn't make sense to have a minimum distance bigger than half the length of the code, because then we will just end up with one code word. So yeah, let's take a look at this guy. What does this mean? So why do we want this to be a fraction of, or multiple of n, or fraction of n? We want this essentially to be independent. The minimum distance, we want the minimum distance to grow with n. Because if we double the size of our code, we also want to double the number of correctable errors. So if we have a certain minimum distance for the short code, we double the length of the code, the minimum distance should also double. So the minimum distance should be a function that is linear in n. If n doubles, minimum distance should double. If n triples, minimum distance should triple, because the fraction of errors that we want to correct per bit should stay the same. So that's why we require the minimum distance to be multiple of n. Okay, so now what is this probability? So what is the probability that the minimum distance is upper bounded by delta n? And that's given again by this quite technical expression. And again, the derivation makes use of the previous approximation. You see this in the exponent that looks a little bit familiar. And the proof is also lengthy, and we put it in the supplementary material because it's not so important for the remainder of the lecture. It's if you want to go really deep into the analysis of these codes, then it's a very nice proof to look at and very insightful. But for the general lecture, it's put in the supplementary material, which is not relevant. So what does this mean? So let's take a look at this function. So we calculate this upper bound on the probability that the minimum distance is upper bounded by delta n. And we see the following. So if we increase n, so here we see that n goes from 20 to 1000. And if we increase n, we see that we get a very sharp behavior. So we get essentially like a step function. So it means that the probability, if we increase n and n is equal to 1000, the probability that the minimum distance is upper bounded by 0.06 times n is smaller than 0. And this is actually quite nice, because it tells us with very low probability, with a negligibly low probability, we have a minimum distance that is smaller or equal than 0.06 times n. And this means that the minimum distance will likely grow with n. Minimum distance will be somewhere in this region. We don't know where, but at least it will be here, because here we have this very sharp behavior. And we have a probability that the minimum distance is small. It gets small with increasing length of the code. So let's take a look at an example. So if n is large, what does this mean? If n is large, it means that the probability that the minimum distance smaller or equal than delta n is approximately equal to 0 if n, or if delta is smaller or equal than 0.062, and 1 if delta is larger than 0.062. So what I missed to say is that here we have a code of design rate 1/2. So this curve obviously depends on the design rate. Depending on what design rate you have, this will shift, but the general behavior will be similar. So if you increase n, this will approach like a step function. So we have this, and let's take a look at an example. Let's take an example of n equals 110,000. So that means that the probability that the minimum distance will be smaller or equal than 620 is approximately equal to 0. So with a very high probability, we have no code word of weight smaller than 620 with very high probability. And let's take a look. So this depends on A bar W was n choose W times 2 power minus n times 1 minus the rate. So if W is, essentially what it means is if W is small, then this guy will have no effect and this exponent will dominate this expression. So this is something very small, this is something very large. So the question is which one is dominating? Now, if you're looking at a weight of less than 620, this one will be dominating. This one will push this expression down, and this will have no chance of pushing the expression up. And on the other hand, if the probability that the minimum distance is larger than 620 is smaller or equal than 1, so we cannot say anything. So means there could be a code word of weight 621, but we cannot be sure. Because then this guy will, the first guy in this product will start dominating the process. And we're not sure which one, if they even out themselves, this is something we cannot say. We can just say if we are in this region, this guy will dominate for sure and will push everything to probabilities very close to 0. What we also have is that if n grows, then the minimum distance grows likewise. So for instance, if n is equal to, say, 100,000, that means that the probability that the minimum distance is smaller or equal than 6,200 is approximately equal to 0. So then we have a really, really big minimum distance, and the number of codes or errors that we can correct gets very, very small. Okay, so this is what this distance bound tells us. So we have this sharp behavior, and this sharp behavior tells us if we choose n sufficiently large, the chance that we have low weight code words gets very small, and the probability that we have a good or high minimum distance gets very large. High minimum distance also means the probability of doing maximum likelihood decoding gets very small. So we could, for instance, insert the probability, this average weight, this enumerator, inside the Bhattacharya bound that we had, and then we see that the error probability goes down if we increase n for a certain channel. Okay, so with this, we have concluded the introduction to parity-check codes. What we're going to do next is we're going to look at maximum likelihood decoding for the binary erasure channel, because that turns out to be very insightful, and it also is a channel where maximum likelihood decoding is actually very practical. We're not going to do this in this video. We're going to do a separate video for this because it is of fundamental importance and therefore it warrants its own video. So thanks a lot for listening to this video, and see you in the next video where we're going to look at maximum likelihood decoding for the binary erasure channel in detail.